Section 1.1, Properties of Real Numbers. To locate and identify irrational numbers at the approximate location on a number line and to compare and/or order any real numbers. Let's begin by taking a look at the subsets of real numbers. Here we have the natural numbers. The natural numbers are our counting numbers. They start at the number 1, 2, 3, and continue on to infinity. The whole number is a set of the natural numbers, but includes the numeral 0. So the set of whole numbers is 0, 1, 2, 3, and then continue to infinity. The integers is the natural numbers and their opposite numbers, and this also includes 0. Therefore, it has negative values. -3, -2, -1, 0, 1, 2, and 3. And they continue to infinity on the negative and opposite end, which would be the positive end. The rational numbers are all numbers that can be written as quotients of the integers, or in other words, they can be written as a fraction. But the key to remember here is rational numbers can be written as repeating or terminating decimals. So let's take a look at some examples. For example, 5 is a rational number because it can be written as a fraction, 5/1. 0.2 is a rational number because it can be written as a fraction, 2, and this represents tenths position, 2/10, and can be simplified to 1/5, but in this case it's still a rational number. 4 and 1/5. That can be represented as a rational number because I can write it as just a quotient or fraction. 4 times 5 is 20 plus 1 is 21/5. Irrational numbers are numbers that cannot be written as quotients of integers. If a positive rational number is not a perfect square, as 25 or 4/9, then its square root is irrational. Also, irrational numbers are numbers that can be written as decimals but are non-repeating. Therefore, pi, 3.14 is the approximation, but it continues to infinity without repeating. Therefore, this is irrational. The square root of 3 is not a perfect square. Therefore, it is irrational. All non-perfect squares are irrational. This diagram represents the set of all real numbers. On the left, you can see that we have the natural numbers, and that is contained inside the whole numbers, which is contained inside the integers, and those are all rational numbers. On the right side are the irrational numbers. Again, the irrational numbers are numbers that cannot be represented as a fraction, and they are decimals that are never ending and also never repeating. On the next slide, they want us to determine which sets of numbers does each number belong to. Number 1, 0.15. Natural, whole, and integers do not include decimals, therefore 0.15 is not in those sets. It is a real number, and also it can be written as a fraction. 0.15 is 15/100. Therefore, it is also rational. Number 2, 4 2/5. Decimals and fractions are not included in natural, whole, and integers. Therefore, this is a real number. And can be written as a fraction. 4 times 5 is 20 plus 2 is 22/5. And therefore, it is rational. Number 3, the square root of 16, when you simplify, is 4. Therefore, that would be included in the natural numbers, the whole numbers, the integers, and the real numbers. Also, that can be written as a fraction, which is 4/1. Therefore, it is also rational. Number 4, the square root of a -5 is not a perfect square. Therefore, this is an irrational number, but it is real. In the next example, they want us to determine if a pilot uses the formula d equals the square root of a squared plus 7,090a to find the number of miles d that can be seen when flying at an altitude of a miles. Which set of numbers best describes the values for each variable? For the value of a, the altitude, it's going to be a real number. Unless it's a perfect integer, then it would be a whole and a natural. But odds are this is going to have some decimal or fraction involved in it. And if it's real, it's also going to be able to be written as a fraction in this case, since it's going to be a decimal that's non-repeating and not ending. And therefore, this can be rational. For d, it's going to be a square root of that real number. Probably not going to be a perfect square. Therefore, this will be real, but irrational. On the next one, they want us to graph the numbers -3/4, the square root of 7, and 3.6 on a number line. Here we're going to use an approximation to plot those numbers on the number line, starting at 0 and just setting in a few numbers to approximate what is given to me. Here, a -3/4. That is going to fall between 0 and a -1, a -3/4. The square root of 7 is going to be less than 3 because we know that 3 squared is 9. The square root of 9 would be 3, so this has to be between 2 and 3. So therefore, this is going to be approximately the square root of 7. And then we have 3.6, which we can approximate pretty easily. Our next set of examples wants us to compare the values by using a less than symbol, a greater than symbol, or an equal symbol to make the sentence true. Number 1, a -12 and a -38. We know the farther left you go, or the bigger the negative value gets, the smaller that actually gets. So therefore, a -12 is greater than a -38. Here, the square root of 7 we know has to be less than 3 because we know that 2 squared is 4 and 3 squared is 9 and 7 falls in between there. Therefore, this has to be somewhere between 2 and 3. While 10 is greater than the square root of 9, which we know the square root of 9 is 3. Therefore, the square root of 10 is greater than the square root of 7, or the square root of 7 is less than the square root of 10. Here we have 0.4, which we know is 4/10, which can be simplified to 2/5. Here we have 12/30, and if I divide the top and bottom, or the numerator and denominator, by 6, I'm going to end up with 2/5. Therefore, these two values are equal. Our first definition on this slide is the additive inverse. The opposite of any number a is a -a. Number 4, and I want its opposite, I would just make that a -4. If my number is a -3 and I want its opposite, that would be a -3, which we know simplifies to just 3. Also, the sum of a number and its opposite is 0. Therefore, 4 plus a -4 is 0. Multiplicative inverse is the reciprocal of any non-zero number. A is 1 over a. Therefore, if I have the number 3, its multiplicative inverse is going to be 3 over 1, therefore 1/3. If my number is 3 2/3, its fraction is 3 times 3, which is 9, plus 2 is 11/3. Therefore, its reciprocal is going to be 3/11. If I have 0.2, that is actually 2/10, or 1/5, when you simplify, and its reciprocal is 5 over 1. And here, the product of a number and its reciprocal is 1. Therefore, if I have 3 times 1/3, making a fraction out of the first one, I can cross simplify or multiply across. In either case, when I do simplify, I will get 1. Find the opposite and reciprocal of each number. In this case, I want its opposite. Therefore, that is a negative 4 1/3, which is just 4 1/3. And the reciprocal, I must generate a fraction out of this. 4 times 3 is 12, plus 1 is 13/3. And its reciprocal is 3/13. And let's not forget that these are both negative. Here, the opposite of 5 is a negative 5. And the reciprocal of 5, 5 over 1, is 1/5. On the next slide, we have the properties of real numbers. The first one, closure. A plus B is a real number and A times B is a real number. Therefore, this just tells us when I add or multiply real numbers together, I still am going to stay inside the realm of real numbers. The commutative property means to change order. And anytime you change order in a mathematical sentence, that is the commutative property. Here, A plus B equals B plus A, or A times B equals B times A. The associative property never changes order. This regroups. But on the associative property, we must know that the order remains. So here you can see A, B, and C, and again, A, B, and C. They just grouped the A and B in the first set and B and C in the second. Again, A, B, C on both sides. They just regrouped the A, B, and the B, C. Identity gets you back to where you started. And to do that with addition, I add 0 to any number, and I get what I started back. Again, with multiplication, it's similar, but here it's multiplying by 1. If I start with A and multiply by 1, I get what I started with. Inverse. We discussed that on the previous slide. With addition, we take the number plus its opposite, and your solution is 0. And with multiplication, we take the number times its reciprocal to end up with 1. And finally, the distributive property. Here, I'm going to have a number times a quantity. And what I do to use the distributive property is multiply A times B, bring over the symbol that's inside. Here it's a plus sign, it could be a minus, and then A times C. The next slide wants us to name the property of real numbers illustrated by each equation. Number 1, 0 plus 1 equals 1 plus 0. This looks like it could be identity, but all they did is change order. So this is commutative property. Number 2, here 3, 4, 5, here 5, 3, 4. So notice they look like they regrouped by changing the parentheses, but they didn't. They did change the order. So again, this is the commutative property. Number 3, 5, 3, 4, 5, 3, 4. Here the order remained the same, but the grouping of the parentheses changed to contain 3 and 4 and 5 and 3. So this is associative property. Number 4, 3, 8, 1, and just 3 times 8. Therefore, this is multiplicative identity. Anything times itself gets you back what you started. Here, 3 times 2 minus 3 times 7. And here we have 3 outside the grouping of parentheses. This would be the distributive property. Just multiplying each term by 3, leaving the symbol in between the same. Number 6, 3 minus 5 plus 0. When I add 0 to any quantity, I get back with what I started, which is 3 minus 5. Therefore, this is additive identity. Our last definition, absolute value of a real number, is the distance a real number is away from 0 on the number line. Therefore, if I would say we want the absolute value of a negative 3, we only want to know how many units away 3 is from 0. And the absolute value of 3, and this is the notation we use to represent the absolute value of 3, how far away from 0 is a negative 3? It is 3 units away. Therefore, we don't care whether it's positive or negative. We just need to know the distance. Again, if I would choose a positive 6, I want to know the absolute value of the positive 6, and that would be 6 units away from 0. So the absolute value of 6 is 6. Also notice, when you perform the operation of absolute value, you drop the symbols and leave only the positive value of the inside quantity. Let's take a look at a couple of expressions. They want us to simplify these absolute values. Number 1, the absolute value of 3 2/5 is 3 2/5. Notice the absolute value symbols are gone. Here, the absolute value of a negative 5.6 is 5.6. 3 is a little bit different, and inside I have an expression that I have to simplify first. So I bring down the absolute values, simplify the inside quantity, a negative 5 plus 3 is a negative 2. Then I take the absolute value, which is a positive 2. So this tells you I can only take the absolute value of one quantity. So I simplified that to one quantity. Number 4, I bring down the negative value on the outside of the absolute value. Then I have a quantity on the inside, drop the absolute values. 3 minus 7 is a negative 4. The absolute value of a negative 4 is 4, but I need to bring down the negative that's in front of the absolute value. So here my solution is a negative 4. Multiplying, since these are singular quantities, the absolute value of a negative 2 is 2, times the absolute value of a negative 6 is 6. 2 times 6 is 12. Notice I didn't multiply these together first because each absolute value only held one quantity. Here, the absolute value of a negative 3 is 3. Bring down the minus sign. The absolute value of a negative 8 is 8. 3 minus 8 is a negative 5. Notice the difference between these two expressions. Here the quantity is surrounded by the absolute value, therefore I have to simplify to a single quantity. Here, each absolute value has its own term. Therefore, I can perform the absolute value operation.